Hi everyone, in this lecture we're going to discuss the last topic in this module, which is to learn how to construct the shear and moment diagrams using the relations. As I mentioned in the earlier lectures that constructing the shear and moment diagram using these relations to some extent are very helpful as long as we can calculate the area under certain shape. Okay, and in this lecture I'm going to develop 6 rules that we can apply to construct the diagrams. Okay, and in here you will see that how come that calculating the area of certain shapes can help us in constructing the shear and moment diagrams. Okay, let's get started by sketching a section of the beam. Okay, and then on this beam it is subjected to distributed load, okay, with function wx describing how the load is distributed. Okay, and then let's say that the section of the beam in here has a length dx, so it's infinitesimally small. Okay, it's very small, and we can sketch the internal forces on the left end of this section of the beam as m and v, and notice that I draw everything in here in positive sign conventions, and we can draw the internal forces on the right end of the section of this beam as m plus dm and v plus dv. This dm and dv is the change of the moment because it is located at a certain distance away from this first point right here. Okay, and then let's call this point as point 2, point 1. Okay, and as I take some of the forces in the y direction, I can write my equations as v minus v plus dv minus wx times dx equal to 0. Okay, and notice that in here this is the resultant r, right, which is wx dx. Okay, and as we simplify these expressions, right, and as we simplify these expressions, we will obtain negative dv minus wx dx. Okay, and in here dv is equal to negative wx dx, and we obtain that dv dx is equal to negative wx. Okay, so this wx in here is as w as a function of x instead of w multiplied to x. Okay, so please differentiate. And we are going to use this expression, okay, to state our first rule, that the slope of the shear diagram is equal to the negative of the ordinate of the distributed force. Okay, so the slope of the shear diagrams is equal to the negative of the ordinate of the distributed force. Some of you may ask, what is ordinate? So if you can remember what you have learned in calculus, when you plot the diagrams, you have x and y. Another terms that we can call this x and y, we can use axis to call x and ordinate to call y, right? So this ordinates basically, is the y axis. Okay, and I think it will be clearer once we discuss some example problems later. Okay, and from these expressions right here, okay, we can further rearrange the expressions or let's say that we use this expression right here, right? So we have dv is equal to dx. Taking the integrations at both sides, we will obtain the change of the shear, okay, is equals to these integrations, okay? And if you can recall what is this integration means, it actually means the area under the curve, okay? Or in this case, under Wx, okay? So this gives us the second rule, that the change in shear is equals, okay, to the negative of the area under Wx, under the distributed force, okay? So this is the second rule, okay? Then we can form the third rule by first taking the sum of the moment at point 2. We will have in here is negative m plus dm, right? And then we have negative v times dx, okay, right? Then we have plus r times dx over 2, okay, which is here we assume is dx over 2, okay, and set this equal to 0, right? We know that this can be cancelled out, right? So we can write my dm is equal to v dx plus r is w of x dx times dx over 2, right? So I obtain my dm is v dx plus wx dx squared divided by 2, okay? And since we know that dx is very, very small, right? And the square of something that is very small is even smaller, so we can ignore these terms, right? Because it's close to 0, right? So finally, we got the final expression that in here, dm is equal to v dx, okay? And with that, I can form my third rule in here, which is dm dx is equal to v, okay, which is I move this dx to the left hand side equation, okay. So this third rule tells me that is the slope in the moment diagram is equals to the ordinate of the shear diagram, okay. And then I can further use this expression in here, dm v dx, and take the integrations at both sides. I obtain in here is the change of the moment is equals to this integration, okay. And basically this is our fourth rule, right? In plain English, it says that the change of moment, or the change in moment diagram, is equals to the area under shear diagram, okay. And from these 4 rules over here, you already start to see why we need to be able to calculate the area under certain shapes, because in here we need to calculate the area under the shear diagrams. In here we need to calculate the area under the distributed force, Okay, and all of these rules will be much clearer once we discuss an example problem. Okay, and another two rules that I would like to state in here is that when I have a section of the beam, right, and this section is very small again, and we call it dx, and the internal forces at the left end of the beam is m and v, and then the internal forces on the right end of the beam is m plus delta m, and then v plus delta v. Okay, and then let's say on this small section of the beam we have applied load F, and let's assume that it's going upward. Okay, and if we take some of the forces in the y, here we have v minus v plus delta v plus F equal to 0. Okay, we know that in here we obtain that delta v is equals to right, and then delta v is equals to F. Okay, and this is basically the fifth rule. So this basically says that shear diagram will jump. Okay? When I mean with jump, it will move upward. Okay, upward if F goes upward. Okay, and of course, on the contrary, if F goes downward, then delta V, the change in the shear diagram, it will goes downward also. Okay, it will change, goes downward as well. Okay, with the amount equals to the magnitude of the force. Okay, and the last rule is that when we have, let's say, a moment, a discrete couple applied at a section of the beam, let's call that length of the section is dx, and here we have mv, here we have m plus dm, v plus dv, right? Taking some of the moment of delta m, delta v. Taking some of the moment at point 2, right? And if this is point 1, right? We obtain negative m naught plus m plus delta m equal to 0. Okay, and of course we have in here, it's not complete yet, we have plus negative v times dx equal to 0. Okay, and with this, right, we can cancel out these two terms. Okay, so we have delta m minus m naught minus v dx is equal to 0. Okay, and since dx is very small, right, we can neglect these terms right here. Okay, thus we can write our final expression as delta m is equal to m naught equal to 0. So delta m is m naught. Okay, and this is to indicate the sixth rule, which state that the change, the moment diagram will jump upward if the applied external moment is clockwise. Alright, So those are the 6 rules that we are going to learn how to apply it in the next lectures, and I think that's enough for this lecture. And if you have any questions, please let me know. Okay, and thank you for listening.